This question is testing you on organic chemistry. In the question, they give you 3 compounds X, Y, and Z, and they went on to tell you that they are isomers. So the very first thing that you need to recall in the chapter of Intro to Organic Chemistry is that isomers are organic compounds with the same molecular formula, all right, but different structural formulae or different structures or arrangement of atoms. So for the first part, the question is asking you, they are given several pieces of information on the 3 compounds, and which information tells you or best supports that they are isomers. Personally, I find this question a bit ambiguous or debatable. Reason being, to show that they are isomers, you actually need a combination of 2 pieces of information in the table to tell that they are actually isomers. Remember, isomers have same molecular formula, so therefore they would have the same empirical formula as well. All right, but compounds having the same empirical formula, does it necessarily mean that they would have the same molecular formula? The answer is no. So the only way that we can conclude that they have the same molecular formulas is by combining the empirical formula with the relative molecular mass. Because when they have the same empirical formula and they have the same molecular masses, it means that they have the same molecular formula. All right, so no one isolated piece of information is able to tell you that they are isomers. However, given the context, the information that best supports would be empirical formula. All right, reason being, you have compounds having the same molecular same molecular mass. It doesn't tell you anything much. For example, nitrogen and carbon monoxide and ethene have the same molecular mass. However, they are very different molecules. All right, so the information that best supports that they are isomers would be empirical formula. All right, but to confirm that they are isomers, you need a combination of both empirical formula and relative molecular mass. The next part requires you to make use of the information in the table to draw the structure of compounds X, Y, and Z. So let's take a closer look at the pieces of information they are given. You are given the number of the different fragments in the compound. So they show you certain fragments of the skeleton of the compound. This is going to be useful because it tells you how the carbon atoms are going to be connected together to form the backbone. Okay, you're given the empirical formula, you're given the molecular formula. Earlier, I've already mentioned that with the combination of the 2, you can actually find the molecular formula. Okay, you are also given the pH of the solution of compounds X, Y, and Z. Now this seems like an irrelevant piece of information at this point in time, but for Cambridge, for O-level questions, every piece of information given would be needed. So they will not give redundant information to throw you off your tracks. Okay, bear in mind that. So when you look at an O-level question, every piece of information given would be helpful or would be needed to solve the question. Okay, so later on we will see how pH comes into play for us to solve this question. Now, before we can draw the structure or the structural formula for each isomer, very importantly, we need to know the molecular formula first. Okay, and how do we obtain the molecular formula? This goes back to mole concept, where we learn that using mass information we can find empirical formula. And then after finding empirical formula, given the relative molecular mass, we can therefore find the molecular formula. How do we do it? Is to recall that molecular formula is n times of your empirical formula, where n is an integer. So the relative molecular mass would be also n times of the mass given by the empirical formula, meaning 12 times 2 plus 4 plus 16. Okay, with that you will find that n equals to 2, and the molecular formula for compounds X, Y, and Z would be C4H8O2. Alright, so the structures that we draw for X, Y, and Z must contain 4 carbons, 8 hydrogens, and 2 oxygens. So now let's try to draw the structure of X. Structure of X, we are given that there is one methyl group, CH3. Now for such a fragment, it must be found at the end of the carbon skeleton, or it must be found at the end of the organic compound. Why? Because carbons can only form 4 bonds. So that means that this carbon can only be connected to one more carbon atom. Alright, and therefore it cannot be found in the middle of the chain. Okay, then you are told that there are 2 of these CH2 fragments, which CH2 fragments are usually found in the middle of the chain. Again, why? Because carbon can form 4 bonds. So if it's only bonded to 2 hydrogens, means that carbon can form 2 other bonds. Okay, and lastly, we have this group over here. Alright, now if we were to count the number of hydrogen atoms, you would find that at this point in time we have only 7 hydrogen atoms, so we are short of one more, and the logical place is to put it here. Alright, once you have established the structure of X, it immediately becomes obvious the relevance of pH in the table. Why? Because we are looking at a carboxylic acid. Alright, so carboxylic acids, as we have learned, they are weak acids, so therefore that explains why the pH of X is around 3. With that in mind, if you look at Y also has a pH of 3. That means that structure Y must also be an acid. Okay, Y is also an acid. Let's look at the other groups present. We have no CH2 fragments. Okay, we have no CH2 fragments, but we have 2 CH3 fragments as shown over here. Remember, your CH3 fragments must be found at the end of the chains. So the only way to do it is like this. So we can have CH3, and then we have another CH3. Okay, now if you were to again count the number of hydrogen atoms, or if you look at the number of bonds around each carbon atom, you'll find that this carbon atom, the one that I'm here, is short of one bond or one hydrogen atom. So this is the structure of isomer Y. Okay, lastly, if we look at isomer Z, they tell you that it's insoluble in water, so it cannot be a carboxylic acid. We have learned that carboxylic acids and alcohols, they are soluble in water. So in this case, it cannot be a carboxylic acid, yet it contains this COO group. Okay, it contains a COO functional group, but it's not an acid. Therefore, that immediately tells us that Z must be an ester. Okay, Z must be an ester. Remember, once again, you have 2 CH3 groups. So CH3 groups must only be found at the end. So that suggests that you have one that's here at the end of the compound, or at the end of the chain, or at the end of the molecule. And then if you look at the remaining fragments, it means that we have another CH3 at the other end and a CH2 in between. So this is the structure for compound Z. Okay, now this wasn't mentioned explicitly in the lessons, but esters, essentially esters, are insoluble in water. So for part C, the question is talking about adding magnesium to isomer X and isomer Y. So state and explain. Again, these are 2 important points that you need to have in your answer. You need to state what happens, and then you need to explain why it happens. So in order to solve this question, you need to first recall that X and Y, they are actually acids. Okay, and it's not difficult to identify that magnesium is a metal, and we have learned in acids and bases that metal plus acids will give you salt plus hydrogen gas. So whenever a gas is being produced, you would see effervescence. Okay, so state what you would expect to observe. You expect to see effervescence, or you can just simply write bubbles appearing. Why? Because magnesium is a metal which will react with your X and Y, which are acids, to produce hydrogen gas. So that's sufficient. I think the key phrase here is that hydrogen gas is produced from the reaction. Now there's a subsequent part to the question where they ask you to include reference to the rate of reaction in your answer. Personally, I find this part a bit ambiguous as well, because what does the setter exactly mean, reference to rate of reaction? There are two ways to looking at it. So if I'm a student, I will actually answer both just to make sure that I cover whichever intention that the setter wants. So the first reference to rate is this, that in any speed of reaction, remember at the start of the reaction, the concentration is the highest. So the rate of reaction, or the rate of bubbling or effervescence, would slow down as time increases. Okay, or the rate of bubbling would become less vigorous as time increases. So this is a reference to the rate of reaction with time. Okay, however, the setter could also mean the rate of reaction of isomer X compared to isomer Y. Alright, so in this case, the rate of bubbling would, or the initial rate of bubbling, that means the bubbling at the start of the reaction, would be similar or the same for X and for Y. Now why would I say that they are the same? Because remember, rate of reaction depends on your concentration of ions, or the concentration of reactants. And in this case, if we are looking at hydrogen ions, which is the main ion that is reacting in an acid, for X and Y, they actually have the same concentration of hydrogen ions at the start. And how would I know that? Is again given by a key piece of information in the table, where the pH is equals to 3 for both. That means that the concentration of hydrogen ions in X and Y will be the same at the start. So if the concentration of hydrogen ions are the same, the rate of reaction for X and Y with magnesium would be the same as well. So I have no idea which one the setter intended. Is it the rate of reaction with time, or the rate of reaction between X and Y? And in situations like this, as a student, just to be safe, I would write both.